So our next topic dealing with functions are what we call composition of functions and inverse functions. And you guys have seen a little bit of a taste of this in Algebra 2. Later this semester, I think we'll kind of come back and hit compositions and inverses again. So like it says, we're kind of just looking at a preview of this, but it fits in within our unit dealing with functions. So with that being said, if we have two functions, f of t and g of t, the function f of g of t is said to be what we call a composition of f with g. So that notation might look familiar to you from Algebra 2. Basically what we're doing here is we are taking, okay, so you guys help me out here. G of t represents what? The output. Let's say it again. G of t represents the output. So what we're doing is we are taking the output of function g, making it the input to f. Okay? So we're using the output of function g as the input to f. So what we're going to look at is calculating and evaluating some compositions, and then we'll look at finding expressions for functions that are compositions. So looking at the first example, we have two different functions, f and g, defined. So it's our job to calculate first f of g of 3. So what we are going to start with is we need to find the output value for g of 3. So definitely using skills that we have talked about so far. So to evaluate g of 3, just taking 3, inserting that into the function, and evaluating. So that would be 9 minus 3, which is 6. So when I say f of g of 3, because g of 3 is really 6, this is the same thing now as saying f of 6. You follow? So then what we're going to do next is find f of 6. We're taking the output of function g, making it the input of f. So then substituting 6 into function f. So that would give us 12 plus 1, which is 13. So then we would state that f of g of 3 is equal to 13. Okay, you guys, about 2 minutes. Now I'm asking you to find g of f of 3. Go, talk with your table. is 6. That's a numeric value. I think you're thinking of when we're down here and actually function.
Congratulations.
Okay. Lucas, what did you guys start with back there?
We started off with
Okay, and you found f of 3 to be what? 7, and then what?
then we plugged that 7 into g of f3.
Okay,
And then we got 36.
you got what?
46.
46. There we go. So then we can state that g of f of 3 is 46. Thumbs up? So far, so good? Questions that I can answer? All right, so now on the next two examples, notice there's no input value for x. We're just keeping that as x. So what we're going to do here is take the entire function g, which is x squared minus 3, and substitute that into function f. So let's start with function f, and we're going to start with that 2. And instead of that variable x, let's leave a set of parentheses and then plus 1. Because what's our input now? Emily? Which is x squared minus 3. So then we're going to substitute g into f. And then again, we're just simplifying. So distribute your 2 and then combine like terms. Regan, is that what you were thinking about? Yeah, that's what I figured. All right, let's go the other way now. Now we're taking function f, substituting it into g. So g of f of x equals, now here we have, instead of x, we have parentheses squared minus 3. Reagan, what's going in those parentheses? 2x plus 1, good. All right, we've worked on this little algebra skill quite a bit. Please don't keep making that mistake by distributing that exponent. This is the quantity 2x plus 1 times itself. So I want you guys to take a minute, finish simplifying that down, and I'll be around if you have a question. When you're finished, I want you to compare your work with those at your table. You guys keep wanting to do that.
Wow, my this word sucks. I literally just said that 2 plus 2 is 6.
Welcome to my life.
Yeah, I got 4 in there.
How did you get this work?
So when we were doing this, like for some reason, I was like, okay, 9 minus 3.
All right, guys, let's bring it back together. You are all, guys, you are all looking good here. We should have 4x squared plus 4x minus 2. Okay, I'm going to pick on you. Sorry, Emily. Do not solve. Tell me where it says to solve a quadratic.
Nowhere.
Exactly. You guys wanted to do that on number 2 on your quiz you just got back. You guys want to keep doing it. Stop it.
I like started and then I drew a big X through it.
Good. A big X. Okay. Now kind of looking at applying our composition of functions to a situation that you might find. So we built a new house a couple years ago, and so we had a lot of white walls that we had to paint. And so actually this is something I legitimately did over the summer. Okay. Our goal is to find a formula for the cost as a function of the area to be painted in a room. It says each gallon covers 250 square feet and each gallon of paint is $3.50 per gallon. Let N be the number of gallons of paint needed. So before we can really jump into getting C as a function of the area, we need to kind of use what we have. So let me ask you this. How can we find the cost depending on the number of gallons? How can we find the cost dependent on the number of gallons? Take like 30 seconds, talk with your table. How can we find an equation where cost is dependent on the number of gallons? Go.
Say that again.
Oh, yeah. Because the square root of it is
Drew, how can we find the cost dependent on the number of gallons?
I was thinking you take 3050 divided by 250, so then you get
You're just based on the number of gallons. So it's going to be 3050 N, right? Okay. I think you're a step ahead of me. Now, how do I know how many gallons I need? How do I know how many gallons I need? Divide what by 250? I heard it. A, the area of your room or your walls over 250. So those are the two pieces that we need. Now what we're going to do is we can compose these to be able to write a function C dependent on A. Okay, so we can take our expression for N, substitute it in. And then if you divide and just simplify a little bit here, that 30.50 over 250 is 0.122A. So instead of having to find the number of gallons and then calculating the cost, now you can go right from your area to the cost, okay? All right, kind of switching gears here and looking at inverse functions. Again, you've seen a little taste of this in Algebra 2. So consider a function that describes the cost of a meal determined by the number of sandwiches you buy. So C equals f of s. So my question is, what would s equals f of c represent? 30 seconds to talk over this with your table and then be ready to respond. Go. All right, time. Jack, what did you guys say back there? Sure. So function that describes number of sandwiches. You said based on the amount of money? I'm going to change this just slightly because we need to use the same input and output. So I'm still going to define C as the cost of a meal, but you have the right idea for sure, based on the cost of the meal. So this is just a pretty basic example of two functions that are inverses of each other. And what you can see is we've taken the input and the output and switched them, okay? One thing that's important to note, because we have switched the input and output, the domain of the inverse is the range of the original and vice versa. We say that any function that has an inverse is considered to be invertible. And the way that we denote an inverse is with that symbol that looks like but is not an exponent of -1. So I want you guys to really understand the difference between this notation versus that notation, because those are two very different things in math. This indicates the inverse of function f. Do you guys know what the other notation indicates? This indicates the reciprocal. Here, that is an exponent of -1. So this would indicate the reciprocal, which would be 1 over f of x. That's a very common kind of misconception with notation, so I wanted to be sure to point that out to you guys. Okay. Now kind of getting into the more algebra side of this, actually finding the equation for an inverse. Remember, an inverse is simply when we exchange the input and the output. So when we algebraically solve for the inverse, what we are going to do from this original function is we are literally switching x and y, the input and the output. And then what we are doing is solving for y. So I'm going to start off by subtracting 3 from both sides. And then we are going to divide both sides by 2. Thank you, my dear.
Like 60, right?
Yeah,
Okay.
perfect. I had enough.
60-ish. Maybe a little extra.
That's fine. Now, the only thing that I ask for you to do is go back and make sure that you are denoting that this is the inverse function of f. So we are going to go back to our function notation to show that this is the inverse of function f. All right, let's look at the next one. Same thing. We're going to switch our x and y. And then solving for y. So subtracting 30 first. And then we're going to multiply both sides by the reciprocal of 2/3, which is 3/2. And we're definitely going to distribute that and simplify up a little bit here. So this gives me 2/3 x. When I multiply 3/2 and 30, that would be negative 90 over 2, which is negative 45. And then again, you can go back to your function notation to indicate that that is the inverse of function g. Kyle? Oh, yes. Oh, my goodness. Thank you. Yes. Thank you for pointing that out. Do as I say, not as I do, right? Thank you for that. Other questions or comments? Is this kind of coming back from Algebra 2? A little bit? Okay. Now, the one thing that you really didn't do with inverses in Algebra 2 is evaluate expressions both from a graph, and then we have kind of the same type of thing from a table. It's kind of confusing. I try to kind of show you the thinking that I suggest you go through to make this as least confusing as possible. So with that being said, f of 0, we have done this since, I think, day 1. When the input is 0, the output according to that graph is what, ladies and gentlemen? 5. Okay, so that's nothing new. And actually, the second example is nothing new either. So here we're looking for x values that give us an output of 0. Okay, so negative 2 is one of them. Yeah, like negative 10 is what I estimated that to be. Again, don't forget to get both of those, or however many. Okay. Now we're adding in our inverses. But again, I'm going to kind of show you what I suggest you think through. So we're finding the inverse of f of 0. The inverse of f of 0. So here's what I want you to think about. The input of the inverse is the output of f. So you can kind kind of translate this back and think in terms of what we already know. The input of the inverse is the output of the original function. So this is really saying f of x equals 0, which we know to be what? -2 and -10. Okay, let's look at the next one. So find x for the inverse of f of x equals 0. So again, think back to what this would be in terms of the original function. That 0 would be what? The input of the original function f. So this is the same thing as saying f of 0. Which again we know is 5. All right, you guys have the next two. Share with your table. Libby, what did you get for f of -6? And then what about the next one? It is, because this is really the same exact thing as f of -6. Okay? So when you see that inverse, just think back to, okay, what would this be for the original function? And then it's what we know. Yeah? Okay, so with that being said, I'm just going to give you guys the table with similar expressions like, oh, yes. Oh, yes. So I'm going to give you guys a couple of minutes. I'll be around if you need some help. But with your table, work through those. Go.